Our next presenter is Brandon Clark. I'll tell you about him in a moment here. There we are. From the United States. Brandon Clark is a second-year graduate student at the He's a second-year graduate student in the lab of Dr. William Tarpeh at Stanford University. His focus is on materials design for selective resource recovery from wastewater. And his presentation is selective recovery of ammonia nitrogen from wastewaters with transition metal-loaded polymeric cation exchange adsorbents. So please take it from here, Brandon.
All right. Can you hear me okay?
Yes, we hear you very well.
Okay. Perfect. So, hello, everybody. My name is Brandon Clark. I'm a rising third-year now graduate student in chemical engineering in the lab of Dr. Will Tarpeh at Stanford. And my presentation is on metal-loaded cation exchange adsorbents for selective ammonia recovery from urine. So our main motivation for this work is that current wastewater treatment methods typically take waste from municipal or industrial sources to a centralized plant. Here, reactive nitrogen, for example, ammonium, which is the focus of my talk today, is exposed to microbes that pass it through the nitrification-denitrification pathway, which converts it to unreactive nitrogen gas. This is an incredible waste of energy, in our opinion, since we spend 1% of the world's energy on the Haber-Bosch process to convert gaseous nitrogen back into ammonia, which also contributes to the severe imbalanced input of reactive nitrogen into the environment. So we might as well recover nitrogen in reactive forms when we have it in that form. We could use something like ion exchange materials to adsorb the ammonium into a solid phase that's easy to transport and easier to recover and reuse the ammonium as a value-added product in things like fertilizer, for example. So in order to achieve that, our goal is to make a material that will selectively remove the ammonium in the presence of other common cations, like in urine, like sodium and potassium. But this is difficult. For some background, when an aqueous cation approaches an anionic functional group in ion exchange materials, it will exchange with the current countercation if A, it has a higher binding affinity than that cation, or if the concentration gradient of the target cation is sufficiently high. So looking at the affinity chart on the right, for example, high affinity ions typically have high valency and small hydration radius. And because of this, pure ion exchange is useful, but the selectivity is constrained by these properties. To that end, we developed nitrogen selectivity by replacing ion exchange in these materials with metal ligand exchange. So first, we occupy every anionic site through regular ion exchange with a high affinity transition metal that's capable of inner sphere Lewis acid base type bonding with nitrogen lone pairs. And a metal like that could be copper or zinc, for example. And the photos on the right show the before and after for copper loading. Next, when these resins are placed in an aqueous environment that contains ammonia at an optimal pH range between 9 and 10, ammonia will bind to the resin or the metal itself, while cations without lone electron pairs do not have electrostatic affinity to enough electrostatic affinity to ion exchange with the high affinity transition metal itself. Finally, to recover the ammonium, we introduce acid to protonate the ammonia to ammonium, thus breaking the metal bond for selective nitrogen recovery. However, the proton gradient, concentration gradient must not be high enough to induce widespread ion exchange with the transition metal. And the photos on the right show the copper-loaded resin at these three steps. So in order to prove the selectivity of these materials, we began by doing batch adsorption in equimolar solutions of total ammonia, nitrogen, and potassium specifically, because ammonium and potassium have extremely similar ion exchange properties like valence, hydration radius, and energy. And for equimolar, initial concentration differences can largely be ruled out in terms of describing selectivity of adsorption. And we found when using batch adsorption with a bunch of commercial materials, regular ion exchange materials, and some that we developed, that there is a slight ion exchange preference for potassium, including the initial version of the resin that we metal loaded. So any any total ammonia nitrogen or TAN selectivity that we observed could be possibly attributed to the transition metal presence. What was interesting was we found clear concentration regimes that dictated adsorption. So too low of a TAN concentration caused ammonia to act more like a weak base than a ligand, but too high of a TAN or potassium concentration caused high metal elution due to the combined high ligand exchange and ion exchange pressure on that metal. So the goal was to have a concentration high enough for ligand exchange to occur without ion exchange or outcompeting the resin functional group. So we use two types of weak acid resins containing carboxylate and aminodiacetate groups, and we were able to pinpoint the ideal concentration ranges. It seemed that 200 to 500 MEq per liter provided the highest adsorption capacity, and carboxylate clearly outperformed aminodiacetate for many reasons. More importantly, we found that an equimolar concentration of 200 to 300 MEq per liter provided the highest TAN versus equimolar potassium selectivity. Encouragingly, transition metal elution was only a max of around 2% within this most selective high capacity region. This performance is severely improved over the regular ion exchange resins and can be attributed to the transition metal. But more importantly for this summit, this relates to urine because hydrolyzed urine has a TAN concentration exactly within this optimal range, and any competing cations are below this range, which only improves selectivity compared to equimolar. Furthermore, the pH of hydrolyzed urine is in that optimal range as well, or roughly 9 to 9.2, where this ligand exchange can occur. So to prove the usefulness in urine, we did adsorption with a solution that contained these urine level cation concentrations. And unsurprisingly, we found that divalent cations had non-negligible adsorption despite their relatively low concentration, but adsorption was more selective for TAN over monovalent cations compared to equimolar potassium. But encouragingly, since divalent cations precipitate out largely during hydrolysis, this is good news for hydrolyzed urine, and I have more data on this in a second. So then we want to regenerate these resins and actually recover the ammonium. And when we performed acid regeneration on the resins that had undergone adsorption, we found similar concentration pH phenomena as the adsorption regimes. So too low of a pH would elute both ammonium and transition metal, and too high would preserve metal, but elute too little ammonium to be practical. So therefore, there was another optimum at play, and we found that a pH around 1.35 was optimal for copper retention, and a pH 1.5 was optimal for zinc. And for example, for zinc, we were able to elute at least over 90% of the adsorbed ammonium while eluting around 0.7% of the metal at pH 1.5. And regenerating in the urine solutions, this allowed for high concentration factors of TAN relative to the two monovalent cations, concentration factor meaning the ratio of concentrations of the product solution compared to the concentration ratios of the influent at the very beginning. Therefore, selective recovery was very feasible. So with that, I'd like to thank my advisor, Dr. William Tarpeh, with whom I published a paper regarding this work recently, shown here. And I'd like to thank the people that contributed to my understanding of this idea and the funding sources and the Tarpeh Lab for their continued support. So thank you.
Great, thank you so much. We have a couple of questions here. The first one, oh, they're scrolling, is from Enrique Rodriguez. asking, do you see the potential for organic chemical removal, i.e. pharmaceuticals, in tandem with nitrogen recovery with these resins? Thanks for your talk.
For this type of chemistry specifically, you could probably do organic removal if it has lone pairs like ammonia does. So to make use of that Lewis acid base ligand exchange, you could probably do that here. Yeah.
We have a question from Chris Canaday asking, what is your vision for taking this to scale?
So the good thing about using ion exchange materials is that they are naturally extremely scalable. Having a big, there are very large industrial ion exchange processes out there where it's just a massive column with a lot of resin that you flow through. So this sort of technology is naturally predisposed to good scaling. And so we would envision some sort of column where you would have this resin and then some sort of metal adsorbing resin to collect any of the eluted transition metal. And there's a lot of chelating resins that could do that in some sort of two-step process. That is what we see for scaling.
Great. We have a few more questions, but in interest of time, I think I'll just ask one more, which is for a simplification. Question is, what are the specific inputs and outputs of the ion exchange method, particularly for those who might not be familiar with the norms of that process?
So the specific input into a column of ion exchange material would be hydrolyzed urine. You wouldn't need to modify any more than that. And then what would flow out would ideally be urine, but just solely without as much total ammonia nitrogen. And then in a second step, after that, you would then introduce acid to elute the ammonium, and the effluent from that would, for now, would be ammonium sulfate, but we are looking for other ways of regeneration as well. That is a continuing thing.
Great, thank you.